Yeah, hi everyone. I'm going to explain what is linear programming for CBSE exams and how to programize the given problem in terms of linear equations as well as linear inequations. It is totally application of solving of a system of linear inequations or sometimes linear equations either by using graphs or we can use even matrices to solve the system of equations. So first, let me explain that where to use linear programming and why to use and how to use. It has a very great practical applications in our daily life. For example, here is an example picked from directly CBSE textbook. You see here, a furniture dealer deals in two items, tables and chairs. So a furniture dealer is trying to sell tables and chairs. Then how much he can invest? He has 50,000 rupees to invest. So he has 50,000 rupees to invest uh, in the business to deal with the tables and chairs and has a storage space at most 60 pieces. At most 60 pieces. So storage is not more. Storage is also limited and his investment is also limited. Right. Now you see. All right. A table cost 2,500 rupees. Price of table is 2,500 rupees and price of chair is 500 rupees. Well, so what is the chair cost? Table cost is 2,500. Right. Table price. If you understand the very first example in detailed way, then rest all very simple. 2,500 rupees. And what is the chair cost? Okay. Chair price is equal to 500 rupees. Isn't it? Total investment. Total investment. Total investment is 50,000 rupees. You are going to invest only 50,000 rupees. Right. And capacity of a hall, you can say a shop, whatever it may be, storage. Okay. Storage capacity. Storage space. It can hold maximum 60 pieces. 60 pieces. All right. So now the point is number of items is limited. It is not more than 60. And your investment is 50,000 rupees. And table price 2,500 and chair price 500. Right? Now, if you sell a table, if you sell a table, right, you will get a profit of 2,500 rupees. If you sell a chair, then you will get 75 rupees profit. Well, so here I'll write that profit on table. Profit on table equal to 2,250 rupees. So on each table, you will get 250 rupees profit. And profit on chair is equal to It is 75 rupees. Now, what do you want? We want maximize our profit. We want maximize the dealer's profit. So to maximize the dealer's profit, how many tables he has to buy, how many chairs he has to buy, and those number of pieces should not exceed, and your investment is 50,000 rupees. Right. So that we have to get a maximum profit. Maximum profit. It is a very good example in our practical life. Like you can take a tailor. If you take a tailor, how much time he has to invest on stitching a pant or a shirt, and how much amount he has to spend on each shirt, on each pant, and how much he has to charge, and in a day how many pants and how many shirts he can stitch. These all matters a lot. So here the point is, so what will happen if we buy all tables? How much profit you will get? If we buy all chairs, then how much profit you will get? Or if you buy some tables and some chairs, then what will be our maximum profit? Isn't it? Right. Well, so here you see that suppose if we buy all tables, if we buy all tables, then what will be the profit? If we buy all chairs, then what will be the profit? Well, here you see. Here you see. Suppose dealer decides to buy only tables but no chairs. Only tables but no chairs. Right? He can buy 50,000 by 2,500 rupees because each table cost 2,500. So what is the maximum number of tables he can buy? 20 tables. Right. On each table, he will get 250 rupees profit. Right. So what would be the profit? 250 into 20, that's equal to 5,000 rupees profit if he buys all tables. Suppose he chooses to buy chairs only but no tables. Only chairs. So 50,000 rupees by 500. Then you will get some 100 chairs on each chair. But here the point is your storage capacity is not more than 60 pieces. So you are not allowed to buy 60 chairs. 60 chairs. So therefore, he is forced to buy only 60 chairs. So what maximum chairs he can buy? Only 60. Right. So if he buys only 60 chairs and on each chair he will get the profit of 75 rupees. So total profit is 4,500 rupees. If he buys all tables, he will get the profit of 5,000. If he buys only chairs, he will get 4,500 rupees. Therefore, we have to search the other possibilities, that is the combination of tables and chairs. For instance, suppose if you take 10 tables and 50 chairs, 10 tables and 50 chairs. Well, so he can store maximum only 60 pieces. That's why 10 tables and this. All right. So on each table, you will get 250 rupees. So it is the profit of 2,500. On each chair, you will get 75. Total is 6,250. But we don't know whether it is maximum or not. We don't know whether it is maximum or not. Then what should we do? All right. Done. So is there any mathematical formula to find the maximum profit? Isn't it? So mathematical formulation of this problem. I am going to formulate this problem using linear equations and inequations. Very simple. Every question can be formulated in two variables or three variables. You see that x be the number of tables, x be the number of tables, and y be the number of chairs that dealer buys. Obviously, number of tables and number of chairs cannot be negative. They must be non-negative integers. All right. So here I am assuming that he is buying X tables and Y chairs. So here the first one is that X must be greater than or equal to 0 and Y greater than or equal to 0. This is constraint of non-negativity, right? Non-negativity constraints. Non-negativity constraints. All right. Okay. And second one. See, the number of pieces is maximum 60. The storage capacity of that space is only 60. So therefore, x plus y is less than or equal to 60. Done. And third one. What is his maximum investment? 50,000 rupees. 50,000 rupees. And he is buying X tables. The price of each table is 2,500. So 2,500 into X plus price of each chair is 500 rupees into Y. So his maximum investment is 50,000 rupees. Done. So what I can do is here, I can cancel some two zeros and one 5 also I can cancel so that I will get that 5x, okay, plus y less than or equal to 100. Done. Okay. Now, these are the non-negative constraints. Now you see that these two are known as constraints. These are the constraints on the variables. Constraints. Right? Under these conditions, you have to maximize your profit. Now the last one. What is this last one? That we usually represent it by Z. Z is equal to what is the profit on table? 250 rupees. So 250 rupees into X. Right? Plus what is the profit on chair? 75 rupees into Y. This we have to maximize. This to be optimized. To be optimized. Optimized is nothing but either you minimize or maximize. To be optimized. Either minimize or maximize. All right. This is known as objective function. This is called objective function. Remember, these terminologies are very, very important. Objective function, right? So very basic one is non-negativity constraints, and these are the constraints on x and y. And this is known as an objective function. This objective function must be minimized under the above conditions. Under the above conditions, or you can say constraints. So we have created two variables x and y. X is the number of tables and y is the number of chairs. And x and y are non-negative. And the maximum number of pieces in that hall is 60. So x plus y less than or equal to 60. And your maximum investment is 50,000 rupees. And table cost is 2,500. Chair cost is 500 rupees. So how many pieces totally, how many pieces you can buy? 2,500 into x plus 500 into y less than or equal to 50,000. These two are known as constraints. And the very most important is that we have to maximize our profit. Generally, in linear programming, there are two things that either maximize the profit or minimize the expenditure in general. So minimize the expenditure and maximize the profit. So Z is equal to, usually we denote it by Z, and we get 250 rupees profit on table and 75 rupees on chair. So our profit function is 250 into x plus 75 into y. This is known as an objective function to be optimized. Optimization is nothing but either you minimize or maximize the function. So mathematically, the given problem now reduces to, you say, this is the way we have formulated into mathematical expressions. Maximize z is equal to 250x plus 75y. We have to maximize this. Under which conditions? What are the constraints? Subject to the constraints, 1, 5x plus y is less than or equal to 100. That is the third constraint. X plus y less than or equal to 60. That is the number of pieces in that hall, maximum number of. Second constraint. Third constraint, x and y are non-negative. Non-negative. I wrote the first one. Right. So we have to maximize this objective function, under these constraints. Remember, this is called an objective function. Okay. In generally, why do we call this is linear programming? All variables are linear variables. Right. So thus a linear programming is one that is concerned with finding optimal value, maximum or minimum value, right? Of a linear function, called objective function. Remember, of several variables, say x and y, for the time being, even it can have x, y, z, any number of variables. Subject to the conditions of the variables are non-negative and satisfy set of linear inequalities known as a linear constraints. All right. So these are the linear constraints, and this is non-negativity constraint. Well, the term linear implies that all the mathematical relations used in the problem are linear relations, while the term programming refers that the method of determining particular program or a plan of action. So in order to get a maximum profit, what kind of program we can execute? That is known as a linear programming. This subject is highly useful in higher dimensions in big companies, production companies, where we use many variables, maybe 10 variables or 20 variables, etc. And by formulating the linear inequalities and giving to the system will give the solution. Well, now how to solve this problem? This, how to maximize? This is important, right? So it is easy to see that here each constraint is in x and y. So each one represents a straight line. Each one represents a straight line. This is a straight line. This is a straight line. X greater than equal to 0, y greater than equal to 0 is nothing but first quadrant. Right. So I'll solve this question using graphs. Using graphs. Well, so here we have two basic constraints, x plus y less than or equal to 60. This is the space constraint. And 5x plus y less than or equal to 100, that is investment constraint. And x comma y are non-negative. Here x comma y are known as decision variables. These are known as decision variables. Decision variables. Because they decides profit and maximum and minimum of objective function. Well, so it is very simple that we have to draw these lines, right? Very simple. So we have to draw the two lines, x plus y less than or equal to 60 and 5x plus y less than or equal to 100. So this line is that x plus y equal to 60. And this line is 5x plus y equal to 100. Okay. And anyway, this is origin. Assume this is point A, that is 20 comma 0. And this is point B. We have to solve these two. Directly subtract so that you will get 4x equal to 40 and x equal to 10. When x 10, that y is 50. All right. Now see x greater than or equal to 0. Above means right side of y-axis, y greater than equal to 0, above x-axis. It means that in first quadrant only. And x plus y less than or equal to 60 below the line. And 5x plus y less than or equal to 100 below the line. All right. So here we have that this is our required region. This is our required region. This is the required region. So in mathematical terms, this required region is known as, that is a feasible region. This is a feasible region. And it is a convex. Remember, this is a convex polygon. So in general, we will get that convex polygon. All right. So this is a feasible region. All right. We call this as a feasible region. Feasible region. And outside that feasible region, this is called non-feasible region. Non-feasible region means it is not at all useful for us. Non-feasible region. Right. Now you see that boundaries. This is a polygon. OABC is a polygon. This is assumed C. OA, B, C is a convex polygon. Is a convex polygon. Polygon. The corners of this convex polygon, OA, B, C, are known as corners. OA, B, C are known as corners. OA, B, C are known as corners. Are known as corners. All right. These corners are known as feasible solutions. Right. These corners are known as feasible solutions. These corners are known as feasible solutions. So feasible is nothing but they may help us to maximize or minimize our objective function. Are known as feasible solutions. So we have to substitute each feasible solution in our objective function so that you will get at which corner you will get a maximum profit. This is our motto. Here we have four corners. So we have to substitute each corner in our objective function so that you will find the maximum profit. All right. Here I am going to find that what would be the maximum profit. I am just substituting one value that O. First substituting origin, nothing but you are not buying any chairs, any tables, then you will get nothing. And if you buy only chairs, you will get profit of 4,500 rupees because on each, here the Z objective function. What is the objective function? Okay, corresponding value here I am writing that objective function Z is equal to. What is that objective function? Once again, let me see that objective function is that 250x plus 75. Profit on table is 250, profit on chair is 75. So 250x plus 75y, that is objective function. 250x plus 75y. I am repeating this word many a times. This is known as a objective function. This has to be minimized or maximized. Substitute each corner point in the objective function. At O, we got 0 value. And at 0, 60, you are buying all chairs, you will get 4,500. At B, 10, 50, you will get 6,250 rupees. And at A, you are buying all tables, then you will get 5,000. So this is the maximum. So you will get a maximum profit if you buy 10 tables and 50 chairs. Now you observe how practical it is, isn't it? So this is the situation of learning a linear programming. They will give a word problem. That word problem has to be formulated in mathematical expressions, simply linear constraints, and after that, objective function. And after that, we have to solve the question. I hope you all understand. So what are the basic terminology I have used here? The very first one is constraints, linear constraints, non-negative constraints, and objective function. Objective function, the function which has to be either minimized or maximized. And when you are applying to solve that linear programming using graphical method, you will get sometimes bounded region, sometimes unbounded region. If you get bounded region, that is the bounded one. If you get unbounded region, then that will be the unbounded, right? So generally for unbounded, when you want to minimize the expenditure, you will see the unbounded region, right? When you want to maximize the profit, you will get the bounded region. And this region is known as a feasible region, remember. And the vertices of this polygon are known as corners. These corners are known as feasible solutions. Feasible solutions. And X and Y are known as decision variables. X and Y are known as decision variables. I will explain one more example how to solve and how to make the constraints, how to formulate the given problem in mathematical way. I'll take one more example. Here are a few points. Once again, I want to revise them. Find the feasible region. Find the feasible region of the linear programming problem and determine its corner points, nothing but weights, either by inspection or by solving two equations of the linear intersecting at the point. Right. Lines intersecting at the point. Evaluate the objective function z is equal to ax plus by at each corner point. Capital M, small m be respectively maximum and minimum of that function at that point. When the feasible region is bounded, capital M and small m are the maximum and the minimum values of z exist in general. In case the feasible region is unbounded, open space, unbounded, like if we have a greater than or equal to instead of less than or equal to, well, M is the maximum value of Z if the open half plane determined by AX plus BY is greater than M and has no point in common with the feasible region. Otherwise, Z has no maximum value. Half region is nothing but what is the half plane? Generally, a line divides the plane into two parts. See, for example, if you take this line, okay, above the line is known as half plane and below the line is known as a half plane. That is the meaning of what is meant by half planes. Now I'm going to explain that unbounded region and regarding minimum and maximum of objective function. Here we have a few points. You see that M is the maximum value of Z if open half plane determined by AX plus BY greater than M has no point in common with the feasible region. Right? I'll explain what is this point. You see. Now, let us consider an LPP. We call it from onwards LPP. We call it an LPP. This is a linear programming problem, an LPP. Here, this is an objective function, okay? And the subject to these are the constraints. Well, only the point is how to decide whether less than or equal to or greater than or equal to which region has to be taken. That I'll explain very clearly. First, you draw that 2x minus y equal to minus 5. Put y0, x-intercept minus 5 by 2 and y-intercept is 5. Okay. So here you see that. Where the first one is y-intercept is 5 and x-intercept is this one. You see this one. Y-intercept is 5. So this is the line. Whether we have to take that below the line or above the line, that we have to see. For that, better you substitute origin. Better you substitute origin. If you substitute origin, sir, you see that 2 into 0 minus 0 greater than or equal to minus 5 implies 0 greater than or equal to minus. It satisfies, right? It is satisfied. So you take that region containing that point, containing that point. Similarly, 3x plus y equal to 3. That y-intercept is 3 and x-intercept is 1. All right. So this line, second line. Again, in that, you substitute 0, comma 0. So 0 greater than or equal to 3 is not true. So don't take that containing 0 region. You take not containing 0 region. So above that line. Similarly, 2x minus 3y less than or equal to 12. X-intercept is 6 and y-intercept is 3. This line, right? In this, you substitute 0, comma 0, 0 less than or equal to 12 satisfied. So you take the region containing origin. Containing origin, right? Now you see that entire blue, light blue and dark blue region is the required region. So this is the feasible region. Now, how many corner points we have? How many corner points we have? This is one corner point. This is another corner point. And one here, the letters are given. These are the. All right. So first 0, comma 5. Okay. This is A and B. Assume this is C and assume this is D. All right. Okay. So at 0, comma 5, what is the value of objective function? 100, next 60, next minus 50, next minus 300. Anyway, this is smallest. We want to minimize the function. Remember, we have to minimize the function. Now we have to think that will it be minimum of the function? Is it actually minimum? If there is no other point, which we get less than minus 300, then it will be minimum. Isn't it? Which means that at x equal to 6 and y equal 0, you got minus 300, right? So you got that z is equal to minus 300. That what is z function? Z function is nothing but minus 50x plus 25. Minus 50x plus 20y equal to minus 300. You will get that minus 5x plus 2y is equal to minus that. You draw this line. You draw this line. The dotted line, this line, dotted line. You see, this line has many points common with the feasible region. This line has many common points with this feasible region. So therefore, this function has no minimum value. Has no minimum value. So it has infinite common points. It has infinite common points. With feasible region. With feasible region. So therefore, it has no minimum value. Z has no minimum value. Z has no minimum value. Has no minimum. You see that because suppose if I substitute, you take any point in the region. Suppose x equal to, you take that some x is equal to 6 and y is equal to, or I can take even x equal to 10, no problem at all. Okay, x equal to 10. And you take that y is equal to some 5. Then what is the z value? Z value is equal to minus 500 plus, all right, this is 500 plus 100. you will get that minus 400. Like that, it has no minimum value because that line, objective line has many points common with the feasible region. If it has no common points with the feasible region, then minus 300 will be the minimum value of that function. Remember this point. And what else is left? Will this function have a maximum value? Will this function have maximum value? We can think of it. Will this function have maximum value? Here you say. In the above example, can we say that z is equal to minus 50x plus 20y has maximum value 100 at 0, comma 5. You see, this is 0, comma 5. 0, comma 5. For this, check whether the graph has more than 100 at any other common point, with the feasible region. Yes. This we have to check. Which means that should we get more than 100 by giving some x and y values in the feasible region. In the feasible region. So which means that y has to be more and x has to be less. Y has to be more and x has to be less in that region. For example, you take that x equal to 2 and y is equal to 100. It is there in that feasible region because feasible region is infinite. Feasible region is infinite. I have to check whether that 2x minus y less than or equal to minus 5 or not. Let me check once. This constraint I have to check. What is that? X is equal to 2, y is equal to minus 100. So x equal to 2 minus 100 is not satisfied. Minus 100. No, it's not at all. We have to get something. All right. Minus x equal to 2 I can take and y is equal to something like minus 8. Minus 8. X equal to 2 and 8. Y equal to 8. Let me check once. 2x minus y. So that is 4 and minus 8. That is minus 4 greater than or equal to minus 5, correct? And what is the z value? Here, this z is equal to minus 100 plus minus 100 plus 160 plus 160. Oh, we got only 60. Maybe we have to set some other value. Okay, I'll see that. Well, we have to decide whether z has a maximum or not, right? They said that at 0, comma 5, the value of this objective function is 100. If you can find one point in the feasible region which gives more than 100, then z has no maximum value, right? So you see that for x equal to 1 and y is equal to 8, right? We got that 11 greater than 10. That is absolutely wrong. So therefore, z has no maximum. I have picked a few questions of previous, this is 2024 question, Cbse exam. The solution set of this inequality is, see, this is the strict inequality. So you will get half plane. That half plane whether containing origin or not. Substitute origin. If it is satisfied, then the region containing origin. If it doesn't satisfy, then not containing origin, right? So substitute origin. 2 into 0 plus 3 into 0 less than 6. 0 less than 6. So it is satisfied. So the half region is containing the origin, right? So open half plane containing origin. Over. If it doesn't satisfy, then not containing the origin. Here you see that the maximum value of this objective function subject to these constraints, right? In first quadrant, and there is only one line. There is only one line. So how many points you will get now? You will get only 3 points, isn't it? Well, so I'll just draw the lines. Here x-intercept is 3 and y-intercept is 4. So this is the feasible region. And this point is that 3 comma 0. And this is 0 comma 4. And this is origin 0 comma 0. Right? And this is the feasible region. And this is the feasible region. So you just substitute these corner points. At 0 comma 4, you will get 20. At 3 comma 0, you will get 9. At 0 comma 0, 0. So 20 is the maximum. All right. Here is one subjective question. Without giving any word problem, directly they have given the corner points of the feasible region and asking to maximize the objective function. The corner points of feasible region determined by the points system of linear equations are 0, 40, 20, 40, 60, 20, and 60, 0. The objective function of LPP is given as 4x plus 3y. Find the point of the feasible region at which the value of objective function is maximum and the point at which the value is minimum. Therefore, find the maximum and minimum value. Nothing. Just substitute each function. All right. So here the point and here the value of z. At 0 comma 40. At 0 comma 40, you will get 120. At 20 comma 40. At 20 comma 40. All right. You will get that this is 80 plus 120, 200. Substitute 60 comma 20. 60 comma 20. All right. 240 plus 60, 300. And finally 60 comma 0. That you will get 240. So this is the maximum and this is the minimum. All right. Over. Moving to next question. This is 2023 question. The corner points of bounded feasible region of LPP are given. See, these are the corner points are given. If the maximum value of objective function occurs at A 250 comma 0 and B this, then the relation between A and B. What is there in that? At those points, both maximum values are equal. Isn't it? Substitute 250 comma 0 in the objective function here. So you will get that 500A plus 0 equal to, okay, at this, at A. At B, you will get 400A plus 50B. Nice. This is the only a relation. So therefore 100A equal to 50B. Therefore 2A equal to B. This is the relation. Simple. This is 2023. Solve the linear programming graphically that we have to minimize that 3x plus 8y. Subject to the constraints that 3x plus 4y greater than or equal to 8, greater than or equal to 11, and xy greater than or equal to 0. All right. Okay. So very first one, that 3x plus 4y greater than or equal to 8. X-intercept is 8 by 3, y-intercept is 2. X-intercept is 8 by 3, y-intercept is 2. This one. Right. And the next one, x-intercept is 11 by 5. That is 2.2. And 11 by 2. Like this. All right. So origin A, B, and C. This line is that 3x plus 4y equal to 8. Substitute the origin. Substitute the origin. Is it satisfying or not? No, it is not satisfying. So it is not containing the origin above the line. Above the line, right? So above the line. And substitute origin in the second line. No, it is also not satisfying. So above the line. So which means that now the feasible region is, this is the feasible region. Like this. This is the feasible region. Remember, substitute origin in each constraint. If it satisfies, you take the containing origin. If it is not satisfied, you take not containing the origin. All right. So this point is 8 by 3 comma 0. All right. And this point is second constraint, that is 0 comma 11 by 2. Done. And solve these equations. 3x plus 4y equal to 8. 5x plus 2y equal to 11. You multiply second equation by 2 and then subtract. You will get that minus 7x equal to 8 minus 22, that is minus 14. So you will get x equal to 2. When x is 2, you will get that y is equal to 1. X is 2 and y equal to 1, isn't it? X is 2, that y is equal to 1 by 2. So this point is that 2 comma 1 by 2. All right. So we have to find out the minimum of this expression. Substitute each corner point. Okay, this is known as a corner method. Now, at A, 8 by 3 comma 0. What is the objective value at A? That z is equal to, you will get 8. This is, assume that A, B, and this is the point C. At B, 2 comma 1 by 2. What is the value of z? What is the value of z? Z is equal to 6 plus 4, that is 10. All right, the last point, that is 0 comma 11 by 2. So 0 comma 11 by 2, you will get that z is equal to 0, and this is 44. So this is the minimum. So Z minimum is equal to 8 at at 8 by 3 comma 0. But we have to check that because this is an unbounded region. Okay. For this, what is that constraint? What is the objective function? 3x plus 8y equal to 8. If you can find some other value less than 8, then it has no minimum value. Then it has no minimum value. All right. Okay. So what I will do is that I will draw this line. That y-intercept is 1 and x-intercept is 8 by 3. Y-intercept is 1 and x-intercept is 8 by 3. So I'll draw that line like this. This is that 3x plus 8y equal to 8. You see, this line has no common point with the feasible region except that point. Except this point A, it has no any common point with the feasible region like previous example. You see here. Here you see. This one. It has many points has common with this feasible region, So that's why. So therefore, our question is finished. That's it. So therefore, it has a minimum value 8 at 8 by 3 comma 0. Here is one more example of a diet problem. Of course, actually syllabus has reduced like anything compared to 2022. Here you see a dietitian has to develop a special diet using two products P and Q, each packet containing 30 grams of food P, right, containing 12 units of calcium, 4 units of iron, 6 units of cholesterol, and 6 units of vitamin A. Each packet of same quantity of food Q contains 3 units of calcium, 20 units of iron, 4 units of cholesterol, and 3 units of vitamin A. The diet requires at least 240 units of calcium, at least 460 units of iron, and at most 300 units of cholesterol. How many packets of each food should be used to minimize the amount of vitamin A, not to maximize in the diet? What is the minimum amount of vitamin A? This is the question, right? Okay. So we have to include that calcium, iron, cholesterol, and vitamin A. Well, see, let Xn be the number of packets of food P and Q respectively. Okay. Right. Obviously, X is greater than equal 0 and Y is greater than equal 0. Right. Mathematical formulation of this problem. You see that 6 units of cholesterol, 6 units of vitamin A. Right. So here 6 units of vitamin A of packet A and 3 units of vitamin A of packet Q. We want to minimize that vitamin product, right? So that's why our objective function based on only vitamin, that 6x plus 3y. X is the number of packets of food P and Y is the number of packets of food Q. And that vitamin A in product P and vitamin A in product Q, that has to be minimized. What are the other constraints? What are the other constraints? For product, for food A, you must use 12 units of calcium and 4 units of iron and 6 units of cholesterol. Right? Okay. All right. So we have that 12x because we are using X packets for product B. Okay. So what should be the total calcium has to be used for food B? 12x plus 4y. This is the iron. Okay. Now the diet requires at least 240 units of calcium. So it must be greater than or equal to 240. This is regarding calcium constraint. Calcium constraint. Like we have three constraints, right? So on simplification, you will get that this is 3x plus y greater than or equal to 80. This is calcium. Next, we will use iron. Okay. 4 units for product A. 4 units for product A. 4x. And 20 units. 20 units of iron per product Q. What is the minimum iron? 460 units of iron. 460. Right? This is the iron constraint. Iron constraint. Well, so you can simplify this that x plus 5y greater than or equal to this is 4 ones and 4 15s. Now regarding cholesterol, how much amount has to be used cholesterol in each packet of product P? Here the cholesterol 6 units, right? Whereas for product Q 4 units. So 6x plus 4y, 6x plus 4y, 6x plus 4y greater than or equal to. What is the minimum amount of cholesterol has to be used? This is at most 300 units of cholesterol. At most 300. At most means it is less than or equal to. So at most 300. This is the cholesterol. Okay. All right. So this is the cholesterol. Maybe spelling wrong. No problem. I'll write correct spelling. Cholesterol constraint. So, and here this I can write that 3x plus 2y less than or equal to 150. And x comma y must be greater than or equal to 0. All right. So now what is the objective function? Z is equal. What should be minimized? We have to minimize that z is equal to 6x plus 3y over. So you just draw the lines and you see the feasible region, found bounded region, and substitute each corner point. Well, so this is the way of formulating the word problem.